जी बेटा, अस्सलाम वालेकुम जी। तो टुडे वी आर गोइंग टू सॉल्व अक्टूबर नवंबर 2021 पेपर 42। ठीक है जी। सो द फर्स्ट क्वेश्चन इज रेडियम इज अ ग्रुप 2 एलिमेंट. The predicted lattice enthalpy for radium sulfide is minus 2612 kilojoules per mole. Define delta H lattice enthalpy. तो lattice enthalpy को define करना है. सिंपल सी definition है. It is the energy change which occurs when 1 mole of an ionic solid, 1 mole of an ionic substance formed from its gaseous ions. 1 mole of an ionic substance formed from its gaseous ions. Right, so this is the definition of lattice enthalpy. Now, next part, they're saying some data relating to radium and sulfur are listed. Select relevant data from this list for use in your answer through part B to E. ठीक है जी। तो ये कुछ डेटा आपको गिवन है, आपने इस डेटा को यूज़ करना है आगे नेक्स्ट क्वेश्चंस के लिए. राइट एन इक्वेशन फॉर द प्रोसेस करस्पॉन्डिंग टू द सेकंड इलेक्ट्रॉन एफिनिटी ऑफ सल्फर. सल्फर सेकंड इलेक्ट्रॉन गेन कर रहा है, मीन्स एक ऑलरेडी गेन किया हुआ है. सो सल्फर इंक्लूडिंग स्टेट सिंबल. सो सल्फर S माइनस सेकंड इलेक्ट्रॉन एफिनिटी है, दैट मीन्स ऑलरेडी एक इलेक्ट्रॉन गेन किया हुआ है. इट गेन्स अनदर इलेक्ट्रॉन, इट बिकम्स S2 माइनस. Sulfur exists as S8 molecules in the solid state. Use the data in this question to calculate the enthalpy change for the reaction S8 into S8 solid into sulfur gas. So आपको atomization की energy find out करनी है. This is atomization of sulfur. Right, so we have to find out the energy change which occurs when S8 solid goes into sulfur gaseous form. सो फर्स्ट ऑफ ऑल तो आपको डिसाइड करना पड़ेगा कौन सी एनर्जी वैल्यूज़ हमने यूज़ करनी है. राइट, सो रेडियम की एनर्जी हमें नहीं रिक्वायर्ड. फर्स्ट आयनाइजेशन एनर्जी ऑफ सल्फर नॉट रिक्वायर्ड. अगर आप ये इक्वेशन देखें, एंथैल्पी चेंज फॉर 1/8 मोल्स ऑफ सल्फर S8 सॉलिड गोज इनटू सल्फर गैशियस आइन. तो अगर आप देखें यहाँ पे डायरेक्टली सल्फर सॉलिड जो है वो गैशियस आइंस में कन्वर्ट हो रहा है. राइट, इसमें एटमाइजेशन भी हो रही है, आयनाइजेशन भी हो रही है, और यू कैन से एटमाइजेशन भी हो रही है और इलेक्ट्रॉन एफिनिटी भी आ रही है. ठीक है, तो हम फिर इसको ब्रेक करके देखते हैं, बट पहले हम ये वाली इक्वेशन लिख लेते हैं. तो हमारे पास इक्वेशन क्या आ गई, 1/8 S8 सॉलिड प्लस 2 मोल्स ऑफ इलेक्ट्रॉन्स गेन्स 2 मोल्स ऑफ इलेक्ट्रॉन टू कन्वर्ट इनटू S2 माइनस गैस. सो यहाँ तो ये आयोनाइज्ड फॉर्म में चला गया है, बट अब हम इसको ब्रेक करते हैं. फर्स्ट मतलब डायरेक्टली कन्वर्ट करने की जगह पे अगर हम पहले इसको एटमाइज़ करें. राइट, सो इफ़ वी एटमाइज इट, जो कि हमें फाइंड आउट करनी है. सो लेट्स सपोज वी से के 1/8 मोल्स ऑफ S8, दैट मीन्स वी ओनली हैव 1 सल्फर एटम. राइट, एक मॉलिक्यूल में S8, 1 molecule of sulfur contains 8 atoms of sulfur. So 1/8 of S8 would be 1 sulfur. So that means sulfur gas. So ये जो energy change है, this is delta H. This is what we want to find out, this energy change. Right. So this is the delta H required. कि आपने इसको एटमाइज करना है, एंड देन दिस एटमाइज सल्फर गोज इनटू आयनिक फेज. सो दिस इज द इलेक्ट्रॉन एफिनिटी 1 प्लस इलेक्ट्रॉन एफिनिटी 2. तो ये सारे एनर्जी चेंजेस हम यहाँ पे ऐड कर लेते हैं. तो दैट मीन्स ये दोनों एनर्जी चेंज हम ऐड करते हैं. सो दिस वुड बिकम, ये जो एनर्जी चेंज है ये ऑलरेडी गिवन है. दिस इज प्लस 555 इज इक्वल्स टू डेल्टा H. दिस वी हैव टू फाइंड आउट. नाउ ये एक सल्फर एटम के लिए है. सो X प्लस फर्स्ट इलेक्ट्रॉन एफिनिटी इज -200 प्लस सेकेंड इलेक्ट्रॉन एफिनिटी इज 532. सो X वुड बी इक्वल टू 555 प्लस 200 माइनस 532. So that would be equal to 555 plus 200 minus 532. So 223 would be the required answer, right? This is 223 for 1 atom of sulfur. बट यहाँ पे आप कितने एटम्स की बात कर रहे हैं? 8 मोल्स ऑफ सल्फर, राइट? सो ये आपके पास 1 मोल के लिए आ गया 223. इसको मल्टीप्लाई बाय 8 कर देते हैं. सो मल्टीप्लाई बाय 8, this would be 1784 kilojoules per mole. So this is the atomization of 8 moles of sulfur. ठीक है जी, आई होप ये समझ में आ गई होगी बात. All right, next question is calculate the standard enthalpy change of formation of radium sulfide. रेडियम सल्फाइड की फॉर्मेशन आपने फाइंड आउट करनी है. ठीक है जी. So formation of radium sulfide, that means radium solid formation हमेशा एलिमेंट से होती है in their standard state, and sulfur solid, right? So this gives radium sulfide. All right, or you can write this equation in this way as well, S8 1/8. ठीक है जी, इसको इस तरह से भी लिखा जा सकता है. तो ये एनर्जी हमें फाइंड आउट करनी है रेडियम सल्फाइड की फॉर्मेशन के लिए. ठीक है. सो हम इसको यहाँ पे ब्रेक करते हैं. लेट सपोज रेडियम, ये तो डायरेक्ट फॉर्मेशन आ गई, डेल्टा एच फॉर्मेशन. नाउ व्हाट इफ फर्स्ट वी कन्वर्ट, जो वैल्यूज़ आपके पास गिवन है दैट इज़, ये जो पहली वैल्यू आप देखें, रेडियम सॉलिड से डायरेक्ट गैशियस आयन के अंदर कन्वर्ट हो रहा है. तो एटमाइजेशन आयनाइजेशन दोनों एक साथ ऐड करके दे दिए. तो हम डायरेक्ट रेडियम को जो है वो आयन में कन्वर्ट करते हैं. तो Ra2+ गैशियस, और इसी तरीके से सल्फ़र को भी आयन में कन्वर्ट करते हैं, बिकॉज इसके लिए भी आपके पास इक्वेशन गिवन है 1/8 मोल्स ऑफ S8. यहाँ से आपको सल्फ़र 2- मिल रहा है. ठीक है जी. सो S2- गैशियस. ठीक है जी. तो ये एनर्जी चेंज आ गया आपके पास. और फाइनली ये दोनों गैशियस आयंस व्हेन दे कन्वर्ट इनटू रेडियम सल्फाइड सॉलिड, दिस इज डेल्टा एच लैटिस एंथैल्पी, जो कि हमारे पास गिवन है. लैटिस एंथैल्पी ऑफ रेडियम सल्फाइड इज -2612. ऑलराइट, सो फॉर्मेशन हमने फाइंड आउट करनी है. डेल्टा एच फॉर्मेशन, दिस वी हैव टू फाइंड आउट. सो डेल्टा एच फॉर्मेशन वुड बी इक्वल टू, यहाँ पे आपके पास रेडियम सॉलिड आयनाइज हो रहा है +1619 प्लस सल्फर की जो आयनाइजेशन है +555. सो 1619 प्लस 555 प्लस लैटिस एंथैल्पी ऑफ रेडियम सल्फाइड इज -2612. So that would be equal to 1619 plus 555 minus 2612. So that is equals to -438. So formation of radium sulfide is -438. ठीक है जी. तो ये हमने कैलकुलेशन वाले पार्ट सॉल्व कर लिए. Now the next part of the question is state 2 major factors that affect the numerical magnitude of a lattice energy. लैटिस एनर्जी के मैग्नीट्यूड पे कौन से फैक्टर्स इफेक्ट करने, जो 2 मेजर फैक्टर्स हैं वो आपने बताने हैं. सो द 2 मेजर फैक्टर्स आर, नंबर 1 इज आयोनिक रेडियस. आयोनिक रेडियस बढ़ेगा तो डिस्टेंस बिटवीन आयंस बढ़ेगा, डिस्टेंस बिटवीन आयंस बढ़ेगा तो अट्रैक्शन कम हो जाएगी, तो लैटिस एंथैल्पी डिक्रीज हो जाती है. तो हम कह सकते हैं आयनिक रेडियस इज इन्वर्सली प्रोपोर्शनल टू द स्ट्रेंथ ऑफ अ लैटिस, और इज इन्वर्सली प्रोपोर्शनल टू लैटिस एनर्जी. और जो दूसरा फैक्टर है दैट इज आयनिक चार्ज. और यू कैन से द प्रोडक्ट ऑफ द आयनिक चार्ज. दोनों आयंस का जो चार्ज का प्रोडक्ट है, तो जितना चार्ज बढ़ेगा आयनिक अट्रैक्शंस बढ़ेगी, लैटिस एनर्जी बढ़ेगी. सो ये 2 मेजर फैक्टर्स हैं विच अफेक्ट्स द न्यूमेरिकल मैग्नीट्यूड ऑफ लैटिस एनर्जी. All right, now the next question is, for each factor you have identified in E1, state whether it tends to make the lattice energy of radium sulfide more or less exothermic than that of sodium chloride. ठीक है जी, तो आपने इन दोनों फैक्टर्स को लेकर कंपेयर करना है रेडियम सल्फाइड को विद सोडियम क्लोराइड. रेडियम सल्फाइड को कंपेयर करना है विद सोडियम क्लोराइड. Now radium sulfide, it has a charge of +2 and -2, whereas sodium chloride has a charge of +1 and -1. So charge radium sulfide का ज़्यादा है. So that means the value of radium sulfide would be, पहले हम इसको चार्ज के हिसाब से कंपेयर कर लेते हैं. So we can say that the lattice enthalpy or delta H lattice for radium sulfide will be more exothermic due to higher charge. ठीक है जी. और अब अगर नेक्स्ट हम बात करें विद रिस्पेक्ट टू आयनिक रेडियस. सो आयनिक रेडियस जो है, रेडियम ये सेकंड ग्रुप का सबसे लास्ट एलिमेंट है. सल्फ़र और सोडियम जो है ये फर्स्ट ग्रुप का सेकंड एलिमेंट है. तो रेडियस जो है वो यहाँ पे रेडियम सल्फाइड में आप कह सकते हैं कि कैटाइनिक रेडियस जो है वो बढ़ गया. तो जितना कैटाइनिक रेडियस बढ़ेगा, डिस्टेंस बढ़ेगा, अट्रैक्शन कम होगी. सो वी कैन से दैट द डेल्टा एच लैटिस फॉर रेडियम सल्फाइड विल बी less exothermic due to higher cationic radius. ठीक है जी. तो ये दोनों फैक्टर्स के बेस पे हमने रेडियम सल्फाइड को और सोडियम क्लोराइड को कंपेयर कर लिया. Now the next question is, the lattice energy of sodium chloride and radium sulfide are -771 kilojoules per mole. This is for sodium chloride, and radium sulfide is -2612. So that means radium sulfide की lattice enthalpy more exothermic है, more exothermic. So identify the dominant factor in determining the relative numerical magnitude of the lattice energies of radium sulfide and sodium chloride. So क्योंकि because it is becoming more exothermic, so that means dominant factor is the cationic charge, right? We can say that the dominant factor is here the cationic charge. So ionic charge is the dominant factor as delta H lattice gets more exothermic. बिकॉज अगर ये NaCl से लेस एक्सोथर्मिक होती तो हम कहते हैं कि रेडियस जो है वो डोमिनेंट फैक्टर है. बट बिकॉज इट इज़ मोर एक्सोथर्मिक, दैट मीन्स कि अट्रैक्शंस ज़्यादा हैं, लैटिस ज़्यादा स्ट्रॉन्ग बनेगा, एंड दैट इज़ ड्यू टू हायर कैटाइनिक चार्ज. ठीक है जी. तो ये पहला क्वेश्चन कंप्लीट हो गया. ऑल राइट जी. तो नाउ द नेक्स्ट क्वेश्चन इज इथॉक्सी ईथेन. This is ethoxyethane, C2H5O, C2H5, can dissolve both in water and in octane 1-ol. All right. तो ethoxyethane वाटर में भी डिज़ोल्व हो सकता है, octane 1-ol में भी डिज़ोल्व हो सकता है. The expression and numerical value for the partition coefficient of ethoxyethane between water and octane 1-ol are given. Water and octane 1-ol are immiscible. राइट. सो ये आपके पास इक्वेशन आ गई. दिस इज़ द इक्वेशन ऑफ पार्टीशन कोफिशिएंट फॉर इथॉक्सीथेन डिजॉल्विंग इन ऑक्टेन 1-ol एंड इन वाटर, एंड द वैल्यू ऑफ पार्टीशन कोफिशिएंट इज 6.760 at 20 degree centigrade. All right. In an experiment, octane 1-ol at 20 degree centigrade is added to a solution of ethoxyethane in water at 20 degree centigrade. In an experiment, octane 1-ol at 20 degree centigrade is added to a solution of ethoxyethane. So आपके पास ethoxyethane जो है वो dissolve in water at 20 degree centigrade, and we have added octane 1-ol into this solution. The mixture is analyzed immediately and a value of K partition coefficient is calculated. मतलब जैसे ही आपने ऐड किया फ़ौरन आपने उस मिक्सचर को एनालाइज किया और पार्टीशन कोफिशिएंट की वैल्यू कैलकुलेट की, एंड द कैलकुलेशन इज़ परफॉर्म्ड करेक्टली but the value calculated is 5.625. Explain why the value calculated is less than 6.760. तो अब मतलब बेसिकली आपने जैसे ही ऑक्टेन 1 ओल जो है वो ऐड किया है, लेट सपोज हम कहते हैं कि ये हमारे पास बीकर था जिसमें वाटर जो है वो मौजूद था और इसमें ऑक्टेन 1 इथॉक्सी ईथेन जो है वो डिज़ोल्व था. नाउ व्हाट वी हैव डन, वी have added octane 1 ol in this mixture, and immediately we analyze this mixture. Few ethoxy ethane particles move into octane 1 ol. ठीक है, और आपने फ़ौरन ही जो है वो इसको एनालाइज़ किया और पार्टीशन कोफिशिएंट की वैल्यू निकाली. तो बेसिकली पार्टीशन कोफिशिएंट इज़ द रेशो ऑफ अ पर्टिकुलर सॉल्यूट इनटू इमिसिबल सॉल्वेंट्स एट इक्विलिब्रियम. ठीक है, ये ध्यान में रखें, दिस इज़ एट इक्विलिब्रियम, एंड यहाँ पे आपने इमीडिएटली जो है वो कैलकुलेट किए. सो दिस इज़ द रीज़न वाई वी आर गेटिंग द पार्टीशन कोफिशिएंट वैल्यू लेस देन 6 पॉइंट, बिकॉज द ओरिजिनल पार्टीशन कोफिशिएंट इज़ 6.760 एट 20 डिग्री सेंटीग्रेड, और जैसे ही आपने इमीडिएटली कैलकुलेट किया है तो आपको क्या वैल्यू मिल रही है, 5.625. दैट मीन्स इक्विलिब्रियम अचीव नहीं हुआ. ठीक है, तो वी कैन सिंपली से दैट एज KPC इज़ measured immediately, therefore equilibrium is yet not established, and the concentration of ethoxyethane is in water is higher than what it must be at equilibrium, than what it must be at equilibrium. ठीक है जी, तो जितनी इक्विलिब्रियम पे होनी चाहिए वाटर में अभी इथॉक्सी ईथेन की कंसंट्रेशन उससे ज़्यादा है, तो जिसकी वजह से जो वाटर की कंसंट्रेशन है वो बढ़ जाएगी और KPC की वैल्यू जो है वो पार्टीशन कोफिशिएंट की वैल्यू कम हो जाएगी. ठीक है जी. नाउ नेक्स्ट पार्ट इज़ अ सेकंड एक्सपेरिमेंट इज़ परफॉर्म्ड एंड द वैल्यू ऑफ पार्टीशन कोफिशिएंट इज़ फाउंड टू बी 6.760. तो मतलब सेकंड एक्सपेरिमेंट जो है वो करेक्टली परफॉर्म हुआ, एंड दिस टाइम आपने इमीडिएटली जो है वो वैल्यू कैलकुलेट नहीं की, सो वी गेट correct answer, that is 6.760. The concentration of ethoxyethane in the octane 1 ol layer is 7.62 grams per dm cube. Right, so जब equilibrium अचीव हुआ है at that time octane 1 ol में ethoxyethane की concentration कितनी है, 7.62 grams per dm cube. Calculate the concentration in grams per dm cube of ethoxyethane in the aqueous layer. एक्वस लेयर में वाटर में एट इक्विलिब्रियम इथॉक्सी ईथेन की कॉन्सेंट्रेशन क्या है ये आपने कैलकुलेट करनी है इन ग्राम्स पर डीएम क्यूब. ऑलराइट, इन ग्राम्स पर डीएम क्यूब. सो पार्टीशन कोफिशिएंट इज इक्वल टू कंसंट्रेशन ऑफ इथॉक्सी ईथेन इन octane 1 ol. So octane 1 ol में ऑलरेडी कंसंट्रेशन गिवन है, दैट इज 7.62 ग्राम्स पर डीएम क्यूब, राइट, डिवाइडेड बाय, और वाटर में आपने कैलकुलेट करनी है तो इसे हम अज्यूम कर लेते हैं x. तो पार्टीशन कोफिशिएंट की वैल्यू ऑलरेडी गिवन है, दिस इज 6.760, राइट. सो 6.760 इज इक्वल टू 7.62 डिवाइडेड बाय x, और x इज इक्वल्स टू 7.62 divided by 6.760. So 7.62 divided by 6.760, and this is 1.13, right? So 1.13 इसको हमने राउंड ऑफ कर लिया, so this would be equal to 1.13 grams per dm cube. So at equilibrium the concentration of ethoxyethane in water in grams per dm cube is 1.13 grams per dm cube. All right, next question is 100 cm cube of the octane 1 ol layer is taken and shaken with 100 cm cube of water. तो आपके पास बीकर में 100 cm³ वाटर है, 100 cm³ water, and it is shaken with 100 cm³ of octane 1-ol, 100 cm³ of octane 1-ol. All right, calculate the maximum amount in moles of ethoxyethane that can be extracted into the water. Right, that can be extracted into the water. Calculate the maximum amount in moles of ethoxyethane that can be extracted into the water. Water में कितना extract हो सकता है ethoxyethane if it is shaken with 100 cm³ of octane 1-ol. Alright, तो अब आपने करना क्या है यहाँ पे कि we have to find out कि अगर हमारे पास 100 cm³ octane 1-ol हो और 100 cm³ water हो, तो water में 100 cm³ water में ethoxyethane की extraction कितनी होगी, कितना dissolve होगा. Now we already know this thing that in octane 1-ol, if we have 1000 cm³ of octane 1-ol, 7.62 grams will be dissolved. Right? ये जो information यहाँ पे given है, there's 7.62 grams per dm³ of octane 1-ol. So means कि if we have 1000 cm³ of octane 1-ol, 7.62 grams of ethoxyethane would be dissolved in it. But इस दफ़ा आपके पास कितना वॉल्यूम है 100 cm³. सो अगर 1000 cm³ में 7.62 डिजॉल्व हो रहा है तो 100 में कितना होगा, तो दैट वुड बी डिवाइडेड बाय 10. सो 7.62 डिवाइडेड बाय 10, दिस वुड बी 0.762. सो दैट मीन्स द वैल्यू ऑफ, अगेन वी विल put the formula of partition coefficient. So partition coefficient would be equal to concentration of ethoxyethane in octane 1-ol and concentration of ethoxyethane in water. So that is equals to 0.762, right? And some of it is now moved into वाटर. जब आप इसको वाटर के साथ मिक्स करेंगे तो इसका कुछ पार्ट, सो दिस वाज, ये जो 0.762 ग्राम्स आए हैं, दिस इज़ व्हेन वी हैव 100 cm³ ऑफ ऑक्टेन 1-ol, तो ये इतना डिसॉल्व होगा. ठीक है, बट अगर आपके पास 100 cm³ वाटर भी है तो सम ऑफ इट विल मूव इनटू वाटर. सो दैट मीन्स इसमें से सब्ट्रैक्ट हो जाएगा द अमाउंट ऑफ ethoxyethane which moves into water, वो इसमें से सब्ट्रैक्ट हो जाएगा. सो दैट वुड बी इक्वल टू, लेट्स से हमने कहा कि x ग्राम्स जो है वो मूव कर गया वाटर में. सो एट इक्विलिब्रियम ऑक्टेन 1-ol में कितना रह जाएगा, 0.762 ग्राम्स माइनस एक्स डिवाइडेड बाय वाटर में कितना गया x. सो पार्टीशन कोफिशिएंट की वैल्यू कितनी है वो हमें मालूम है, दैट इज़ 6.760. सो दिस वुड बी इक्वल टू 6.760 x इज इक्वल टू 0.762 माइनस x, और 6.760 x प्लस x इक्वल टू 0.762, and this would be 7.760 x, 0.762, or x is equal to 0.762 divided by 7.760. So 0.762 divided by 7.760. So that is equals to 0.098, round off कर लें तो 2. सो 0.0982 ये ग्राम्स आ गए. सॉरी, हमने मोल्स कैलकुलेट करने, ये जो आए हैं ये ग्राम्स आ गए. सो दिस इज़ 0.09298 ग्राम्स, और इसको कन्वर्ट करना है मोल्स में, मोल्स ऑफ ethoxyethane. सो इफ़ वी कैलकुलेट द मोलर मास ऑफ ethoxyethane, C2H5O, C2H5, दिस विल कम आउट टू बी 74. राइट, अगर आप इसका मोलर मास कैलकुलेट करें, सो डिवाइडेड बाय 74, सो द नंबर ऑफ मोल्स विच वी गेट वुड बी 0.0982 डिवाइडेड बाय 74. सो दिस इज 0.0013, 0.0013 मोल्स ऑफ वाटर, मोल्स ऑफ ethoxyethane विल मूव इनटू वाटर. ठीक है जी, तो ये पार्टीशन कोफिशिएंट का क्वेश्चन हो गया. नाउ द नेक्स्ट पार्ट इज रिलेटेड टू solubility प्रोडक्ट. एन aqueous solution of lead 2 nitrate is mixed with the aqueous solution of sodium iodide. Lead 2 nitrate is mixed with an aqueous solution of sodium iodide. So we have lead 2 nitrate, NO3 mixed with sodium iodide. So double displacement reaction होगा. A yellow precipitate of lead 2 iodide is formed and is filtered out leaving solution X. ठीक है, तो the concentration of lead ions in solution X is 5.68 into 10 power minus 3 moles per dm cube, and the concentration of iodide ion in a solution X is 4.20 into 10 power minus 4 moles per dm cube. Use this data to calculate the value of the solubility product KSP of lead 2 iodide. So lead 2 iodide के लिए KSP की value calculate करनी है. So lead 2 iodide when it ionizes, ये पार्शली आयोनाइज होता है, तो इसके लिए आप KSP की वैल्यू कैलकुलेट कर सकते हैं. सो PbI2, जब ये आयोनाइज होगा, इट डेवलप्स इन इक्विलिब्रियम, वी गेट Pb2 प्लस 2I माइनस. सो KSP की एक्सप्रेशन क्या बनेगी? KSP वुड बी इक्वल टू कंसनट्रेशन ऑफ लेड आइंस इनटू कंसनट्रेशन ऑफ आयोडाइड आइंस स्क्वायर. ठीक है, और KSP की वैल्यू ये हमें कैलकुलेट करनी है. कंसनट्रेशन ऑफ लेड आइन इज़ 5.68 into 10 power minus 3. Concentration of iodide ion is 4.20 into 10 power minus 4 square. Right? और इसको अगर हम solve करें, so the final answer we would get would be 1 into 10 raised to power minus 9. अच्छा, और finally आपको unit calculate करना है. So this is moles per dm cube. And this is moles per dm cube square. So the final unit would be moles cube dm minus 9. ठीक है जी, सिंपल सा क्वेश्चन है पार्टीशन कोफिशिएंट solubility product का. Now next they're saying potassium iodide is very soluble in water. Potassium iodide, Ki, it is very soluble in water. Describe and explain what is seen if a few drops of saturated potassium iodide solution are added to a portion of solution X. Right, so solution X में क्या मौजूद है? lead ions and iodide ions, right? और lead iodide क्योंकि partially soluble है, so we have this equilibrium established in solution X, Pb2 plus 2I minus. तो क्योंकि ये partially soluble है, so we would have a very small concentration of lead ions and iodide ions which they have given us in the question. So this is very small concentration. Now आपने क्या किया? आपने इसमें potassium iodide ऐड कर दिया है. तो क्वेश्चन है कि डिस्क्राइब एंड एक्सप्लेन व्हाट इज सीन इफ अ फ्यू ड्रॉप्स ऑफ सैचुरेटेड सोल्यूशन ऑफ पोटेशियम आयोडाइड सोल्यूशन आर एडेड. सो KI अगर आप इसमें ऐड करते हैं तो क्योंकि ये कम्प्लीटली सॉल्युबल सॉल्ट है, सो इट गेट कम्प्लीटली आयोनाइज्ड एंड वी गेट पोटेशियम आयन एंड आयोडाइड आयन. सो दैट मीन्स द कंसंट्रेशन ऑफ आयोडाइड आयन विल इंक्रीज एंड इट मूव्स बैकवर्ड, द इक्विलिब्रियम शिफ्ट बैकवर्ड and we get more precipitates of lead 2 iodide, which is a yellow solid. So what is seen if a few drops is added? So आपने just simple यहाँ पे observation लिखनी है that we get more yellow solid as Ki will increase the concentration of iodide ions in solution due to common ion effect. The equilibrium shifts backward or on the reactant side and more PbI2 solid will form. Alright जी, तो ये simple सा question था. So this is it for question number 2. Alright जी, so now the next question is, pure water is a very poor conductor of electricity. However, when hydrogen chloride gas is dissolved in water, ions are formed and a current flows during electrolysis. So water on its own is a poor conductor of electricity, but when we add hydrogen chloride gas, the ions are formed and now the current will flow. Okay, now water will act as an electrolyte. So this is the equation HCl, hydrogen chloride gas. When added in water, we get H plus ions and chloride ions. So the overall change after electrolysis is that hydrogen chloride gas is converted into hydrogen and chlorine, right? So when electrolysis occurs, when hydrogen chloride gas entered into water and electrolysis occurs, we get hydrogen gas and chlorine gas. So the equation for this decomposition is that hydrogen chloride gas will decompose into hydrogen gas and chlorine gas. Now, the next part of the question, they're saying that when a current of 3.10 ampere is passed through the solution for Y minutes, right? The amount of current which is passed is 3.10 ampere and current, and for how long? Y minutes. 351 centimeter cube of chlorine are produced at the anode, measured under room conditions. Calculate the number of chlorine molecules produced during the electrolysis. Right, so we have to calculate the number of chlorine molecules produced during the electrolysis. So because the process is happening under room conditions, and we know this thing that 1 mole of any gas under room conditions occupies 24 dm cube of space, right? So we can just simply use this relation. They have given us the volume in centimeter cube. So number of moles would be equal to, we are calculating the mole, number of moles would be equal to 351 divided by 24,000, right? Because it is in centimeter cube, so we convert 24 dm cube into centimeter cube as well. So 351 divided by 24,000, this is 0.014625 moles. But we have to calculate the number of chlorine molecules. So 1 mole of chlorine would contain 6.02 into 10 power 23 molecules. So now we have 0.014625 moles. So the number of molecules would be, we just simply multiply it with 6.02. So that would be equal to 0.08 0.088. So this is equals to 0.088 into 10 power 23 or 8.8 into 10 power 21. So this is the number of molecules which we get when 351 centimeter cube of chlorine gas would be produced at anode. Now the next part is calculate the total number of electrons transferred to produce this number of chlorine molecules. Total number of electrons transferred, right? So when chlorine produces at anode, the half equation would be 2Cl minus, loses 2 moles of electron to give chlorine. So that means the ratio between chlorine gas and electron is 1 to 2. So for this much molecules to be formed at anode, the number of electrons transferred would be double of the molecules. So we just simply have to multiply 8.8 into 10 raised to power 21 with 2. So this would be equal to 8.8 multiply by 2. So that is 17.6 into 10 raised to power 21 or 1.76 into 10 raised to power 22. So that would be the total number of electrons passed or transferred when 8.8 into 10 raised to power 21 molecules of chlorine would be produced at anode. Now the next part is to calculate the quantity of charge in coulombs of the total number of electrons calculated in B. The amount of charge carried by this much electrons. What amount of charge this much electrons will carry? So we know that 1 electron carries 1.6 into 10 raised to power minus 19 coulomb. So if we have 1.76 into 10 power 22 electrons, what amount of charge would they carry? So that would be 1.76 multiplied by 1.6, 2.816 into minus 19 plus 22, that would be 10 power 3. So the amount of charge carried would be 2816 coulombs, right? So this is the amount of charge carried by this much electrons. All right, now the next part is calculate the time y in minutes for which the current flows. Now we have to calculate. Now we know the charge, and they have already given us the amount of current that we have passed through the cell. So if we knew the current and the amount of charge passed, that means now we can calculate the time, because A is equals to Q upon T, or time is equals to Q upon A. Charge passed is 2816 and the amperes are 3.10. So 2816 divided by 3.10, that is equals to 988.387 seconds, but we have to find out the answer in minutes. So just simply divide the answer by 60. So that would be equal to 15.13, right? So this is the number of minutes for which so 15.13. So this is the amount of time for which the current will flow, 15.13 minutes. All right, or 15.15. Okay. Now, the next part of the question, they're saying that standard entropies of 3 species are given in the table. Calculate delta S for the reaction 2HCl, the decomposition of hydrogen chloride. We have to calculate the delta S, change in entropy. So change in entropy is just simply delta S is equals to product minus reactant. Product minus reactant. So on the reactant side, the entropy of HCl is 187 and we have 2 moles of HCl, so that would be 187 multiplied by 2. 187 multiplied by 2, so that is 374. And on the product side, we have hydrogen and chlorine, so 131 plus 223. 131 plus 223, so this is 354. Right, so product minus reactant would be 354 minus 372. 187 multiplied by 2, that is 374. Right, so 354 minus 374, so that would be equal to minus 20. So the entropy change is minus 20. Delta H for the reaction 2HCl goes into hydrogen chlorine. This is the delta H enthalpy change, plus 185. Calculate delta G for this reaction at 298 Kelvin. So the formula for delta G is equals to delta H minus T delta S, right? And delta H is 185 minus temperature is 298 Kelvin into delta S. Now just remember this thing, that delta S here is in joules per Kelvin per mole, and we have to convert it into kilojoules. So this would be 20 divided by 1000. So 0.02 minus 0.02, because it is in minus negative form, minus 0.02. So this would be 298 multiplied by 0.02, 5.96, and minus would be plus, so this would be 185 plus 5.96. So 5.96 plus 185 plus 5.96, so that is 190.96, or simply 190. So this is the delta G for the reaction. Delta G is positive, that means reaction is not feasible at temperature 298 Kelvin. Now predict the effect of increasing temperature on the spontaneity of this reaction. Now just remember this thing, that reaction is spontaneous when delta G for the reaction is negative. So this must be negative. So if we increase the temperature, if temperature is increased, this value would increase. Overall T delta S or minus T delta S will increase on increasing temperature. Minus T delta S will increase, and as delta S is also negative, this delta S is also negative, so minus T delta S would get positive. So minus T delta S will increase and it gets more positive as delta S is also negative. So the feasibility will decrease, or the reaction becomes less feasible, because the value of delta G would get more and more positive as temperature will increase. All right, so this is question number 3. All right, so the next question is, separate samples of 0.01 moles of magnesium nitrate and 0.01 moles of strontium nitrate are heated until completely decomposed to the metal oxide, nitrogen dioxide, and oxygen. So this question is related to thermal decomposition of group 2 nitrates. Now the first part of the question is, state which of these two group 2 nitrate require the higher temperature before it begins to decompose, and explain your answer. So they have given us two nitrates, strontium nitrate and magnesium nitrate, right? We have MgNO3 magnesium nitrate and strontium nitrate. So group 2 nitrates, they get more thermally stable down the group. This is the trend for their thermal decomposition. It becomes difficult to decompose them as we go down the group. So that means strontium nitrate would require higher temperature. Strontium nitrate would require high temperature, as the cationic radius increases, right? Strontium is a larger cation as compared to magnesium, because as cationic radius increases, it would become difficult to polarize the anion, right? And as ion polarization decreases, the thermal stability increases. So the cationic radius increases down the group, and less ion polarization or ion distortion All right, so strontium nitrate would require higher temperature as the cationic radius increases. Strontium is a larger cation as compared to magnesium, and there would be less ion polarization, and it would be more thermally stable. Okay, so the next part of the question is, after decomposition is complete, the 0.01 mole sample of magnesium oxide is taken and increasing amount of water are added to it, with stirring until no solid remains. So we are dissolving the oxide which we get from the decomposition of nitrate. This procedure is repeated with the 0.01 mole sample of strontium oxide. Identify the sample to which most water must be added to cause all the solid to dissolve. So when we add magnesium oxide or strontium oxide in water, group 2 oxide in water, let's say magnesium oxide, when get dissolved in water, we get magnesium hydroxide. So that means they're talking about the solubility of group 2 hydroxide, and they get more soluble as we go down the group. So the first part of the question, that identify the sample to which most water must be added to cause all the solid to dissolve. So down the group solubility increases, so that means magnesium hydroxide would require more water or more amount of water to dissolve. So we can simply say that magnesium hydroxide would need more water to dissolve, right? It needs more water to dissolve. Now the next part of the question is, explain your answer by reference to the solubilities of the products form when water is added to the oxide. So basically strontium hydroxide is more soluble in water, And you should refer to the relevant energy terms in your answer. So the energy terms which are related to this solubility is lattice enthalpy and hydration enthalpy. And we know this thing that delta H, let me write it here, delta H solution is equals to delta H hydration minus delta H lattice enthalpy. And down the group, both lattice and hydration enthalpy decreases. Hydration enthalpy will be decreasing and lattice will also be decreasing as cationic radius increases. The attraction between the ions and the attraction between the ion and dipole, water is the dipole, will decrease. So hydration will decrease and lattice will decrease. But in case of group 2 hydroxides, lattice decreases more as compared to hydration enthalpy, right? As the cationic radius increases, the decrease in the lattice enthalpy would be higher than the decrease in the hydration enthalpy. And lattice hydration enthalpy is a negative term, right? Hydration is the force of attraction. It is the attraction between the water molecules and the ions. So whenever we dissolve a gaseous ion in water, energy would be releasing. So delta H hydration is an exothermic process, and delta H lattice is also the attraction between unlike charges ions. So this is also exothermic, right? So both the energy terms are exothermic and delta H lattice is negative. So this whole term would become positive. Negative of delta H lattice is positive. So if this negative of delta H lattice decreases more than the delta H hydration, so that means the overall answer would be negative, and that makes the delta H solution exothermic. That means more soluble. So we can just simply say that strontium hydroxide is more soluble in water, and the reason why we have to refer to relevant energy terms, that delta H lattice and delta H hydration both decreases as cationic radius increases. But in case of hydroxides, delta H lattice decreases more. So the overall delta H solution gets more exothermic. So delta H solution gets exothermic. And that's why strontium hydroxide is more soluble in water. Okay, so the next part of the question is the nitrogen dioxide given off by the decomposition of 0.01 moles of strontium nitrate is dissolved in water. When we decomposes the group 2 nitrate, the nitrogen dioxide which we get, we dissolved it in water. The oxidizing agent H2O2, hydrogen peroxide, is then added to give 150 cm³ of a solution in which nitric acid is the only nitrogen containing product. Calculate the concentration in moles per dm³ of nitric acid in 150 cm³ of solution. So now we have to calculate the concentration in moles per dm³ of nitric acid in 150 cm³ of solution. So when we decompose strontium nitrate or any group 2 nitrate, let's say strontium nitrate, when we decompose it, we get metal oxide, strontium oxide plus nitrogen dioxide and oxygen gas. And if we balance the equation, we have 2 moles of nitrogen dioxide and half mole of oxygen. So the molar ratio between strontium nitrate and nitrogen dioxide is 0.01. If we have 0.01 moles of strontium nitrate, we get 0.02 moles of nitrogen dioxide. So that means we have 0.02 moles of nitrogen dioxide which was dissolved in water. And as the question is saying that nitric acid is the only nitrogen containing product in the solution, so that means the moles of nitric acid would also be 0.02, right? And the volume is 150 cm³. So we have to calculate the concentration. Concentration is equals to number of moles upon volume. So number of moles 0.02 divided by 150 divided by 1000. So 150 divided by 1000, that is equals to 0.15, and 0.02 divided by 0.15, that is equals to 0.13. So the concentration of solution is 0.13 moles per dm cube. All right. And the next part is the nitric acid present in 25 cm cube of this solution is neutralized using 0.125 moles per dm cube sodium hydroxide. Calculate the minimum volume in centimeter cube of sodium hydroxide needed. Give your answer to 3 significant figures. So we already have the concentration of nitric acid, which was 0.13, and first we would calculate the moles of nitric acid. So moles of nitric acid concentration is equals to number of moles upon volume. So that would be equals to C into V. Concentration is 0.13. Volume is 25 divided by 1000. So that would be 25 divided by 1000 multiplied by 0.13. So this is 0.00325, and nitric acid and sodium hydroxide, they both will react in a 1-to-1 ratio. So that means we have same moles of sodium hydroxide, and the concentration is 0.125 moles per dm cube. So to calculate the volume of NaOH required, volume would be equal to number of moles upon concentration. Moles of sodium hydroxide is 0.00325, the same moles we have calculated for nitric acid, and its concentration is 0.125. So 0.00325 divided by 0.125. So the concentration or the volume is 0.026 dm cube, and if we convert it into centimeter cube, 0.026 multiplied by 1000, so that would be 26 centimeter cube. This would be the required volume of sodium hydroxide. Okay, so the question number 5 is, this question is related to transition elements. So transition elements, they form complex, and molybdenum forms an octahedral complex. So we have molybdenum, it forms an octahedral complex consisting of one molybdenum atom surrounded by carbon monoxide, right? So carbon monoxide is a monodentate ligand. Iron forms an octahedral complex. Iron forms an octahedral complex consisting of one Fe+3 ion and a number of cyanide ions. Cyanide is a monodentate ligand as well. So the first part of question is define the term monodentate ligand. Right, so monodentate ligands are basically those ligands are basically species which transfer their electron pair to the central metal line, which forms the dative bond with the central metal line and which act as a donor in the dative bonding. So a monodentate ligand, there are different types of ligand. Monodentate ligand is a ligand which donate one lone pair to the central metal line. A ligand which donate one lone pair to the central ion or metal ion. All right, now the next part is complete the table by stating the formula and charges of the complex described. Now they have told us about the two different complexes, molybdenum complex and iron 3 complex. Molybdenum is making a complex with the carbon monoxide, and carbon monoxide is a monodentate ligand, plus it is neutral ligand, means it has no charge, right? So, and it is forming an octahedral complex. Octahedral complex means 6 carbon monoxide would be attached to molybdenum. So the formula of the complex would be MOCN6, right? 6 carbon monoxide. 6 carbon monoxide molecules would be attached as a ligand with the molybdenum, right? And it has no charge over it, so the charge of this complex would be 0. And then we have iron 3 complex, and iron is forming a complex with the cyanide ions. Again, it is an octahedral complex, so that means Fe is attached to 6 cyanide ions, right? And Fe has a plus 3 charge. Fe has plus 3 charge, and cyanide is a monodentate ligand which has a minus 1 charge. So that means in total we have on Fe there is plus 3 charge, cyanide minus 1, so minus 1 into 6, that would be minus 6, plus 3, so the overall charge would be minus 3. So the charge on this complex is minus 3. Okay, so the next part is draw a 3-dimensional diagram to show the shape of this iron 3 complex. Iron 3 complex, we have to draw the shape of this iron 3 complex and label one 180-degree bond angle on your diagram. So there are 6 cyanide ions attached to the Fe plus 3 ion, right? And we have to draw the 3-dimensional diagram. So 3-dimensional diagram. So a wedge will represent a bond coming out of the page, and the dotted line means the bond is going away from us, right? So 6 cyanide ions are attached. So 6 of the cyanide ions are attached with the Fe plus 3, and then we have to label one 180-degree bond angle on our diagram. So any bonds, we can select any 2 opposite bonds. So let's suppose this is an angle of 180 degrees. All right, so this is the diagram of this octahedral complex. And the next part of the question is an excess of aqueous ammonia is added. Excess aqueous ammonia is added to dilute copper 2 sulfate solution. A dark blue complex CuNH34H2O2 plus is formed. Write an ionic equation for this reaction. So we have an excess of aqueous ammonia in a dilute copper 2 sulfate solution. So let's suppose if we have this copper 2 sulfate solution, which would be of blue color. So let's say this is copper 2 sulfate solution, aqueous CuSO4, and we have added excess ammonia into it. So excess ammonia, when we add excess ammonia into it, so we get this complex CuNH34 H2O2 plus. So we have to write the ionic equation. So when we have aqueous solution of copper ions, that means we have this complex. Copper makes a complex with water molecules. So we would have CuH2O6 2 plus. So this is the complex we have in aqueous copper 2 sulfate solution, and we have added excess ammonia. So as you can see in the formula that 4 of the NH3 molecules are added into this complex. So that means 4 water molecules would be replaced. So that means we have 4 NH3, and out of these 6 water molecules, 4 will be replaced by NH3. So the new formula that we get would be CuNH3 4 H2O2, and the overall charge still would be 0 because both water and ammonia are neutral and 4 water molecules are replaced. So this is the equation or the ionic equation for this reaction. All right. Now the next part of the question is explain the origin of color in copper 2 complexes. Transition metals, they have this characteristic that they show colored compounds. So now we have to explain the origin of the color. Origin of color in copper 2 complexes. So the color of transition metals is due to the energy separation between the d orbitals. The d orbitals which are degenerated, we have 5 degenerated d orbitals. Let's say these are 5 degenerated d orbitals. 1, 2, 3, 4, 5. This is dxy, dyz, dzx, dx square minus y square, and dz square. So in copper 2 complex, that means copper has total 29 electrons, and when it loses 2 electrons, it is left with 27, and in d orbital it would have 9 electrons left. So that means 1 2 3 4 5 6 7 8 9. So these are degenerated orbitals. This is basically a copper 2 ion. But when it forms complex, when a ligand approach this copper 2 ion, its degeneration breaks. Degeneration breaks, and these d orbitals would split into 2 energy levels. So this degeneration breaks due to the repulsion caused by the ligands to the d orbital, to the electrons of the d orbitals, right? You just have to remember this thing, that degeneration breaks due to the repulsion caused by ligand to the electrons in d orbitals. All right, so this, due to this repulsion, now we have 2 energy levels. These degenerated orbitals, they are divided, they are splitted into these 2 energy levels. So dx square minus y square and dz square, they would become the higher energy level, and dxy, dyz and dzx, they become the lower energy level. So this is the energy separation or orbital split when we get an octahedral complex, copper 2 complexes, or in tetrahedral complexes it would be opposite. dxy, dyz, dzx would be higher energy levels, and dx square minus y square and dzx would be the dz square would be the lower energy level. So for now we would explain the color origin through this energy separation, right? So now we have this energy separation, and the electrons, still total number of electrons would be same. So we have total number of 9 electrons, right? And now there is an energy gap between these orbitals, and this energy gap lies in the visible region of the electromagnetic radiation. This energy gap, this delta E, it lies in visible region. So that means if one of these electrons will absorb energy from the visible region of electromagnetic radiations, it will jump into the higher energy level. So let's suppose if these d orbitals, they get hit by the sunlight, by the visible radiations. Let's suppose if this electron absorbs some of the sunlight, it will jump into the higher energy level. And for that jump, it will absorb some amount of energy, right? So it would absorb some wavelength or some specific frequency of the visible region, and it will jump into a higher energy level. It goes into excited phase, and some part of the energy would be absorbed by it, rest will be transmitted. And that transmitted light, that would be the complement of the color it absorbs, right? And that would be that will be responsible for the color of the complex. So we can just simply say that the d orbitals, they get split as we have shown in the diagram, right? D orbitals, they split when ligands approach them, and the electron absorbs specific wavelength from visible region and jumps into higher energy level. Or it get promoted or excited into the higher energy level, and the transmitted light Some part of the energy would be absorbed for this promotion, and the transmitted light, the rest of light, is the complement. It would be responsible for the color. Transmitted light is complement of color absorbed. So, right, so this transmitted light would be responsible for the color of the complex. So like, let's suppose if it absorbs yellow color wavelength, we get the purple color. The complementary of yellow is purple. You don't have to memorize these complementary colors. If it absorbs red color, then the complementary color would be green, right? So this is how we get colors for the transition complexes. All right, now the next question is, an excess of concentrated hydrochloric acid is added to the dark blue solution of this complex, right? A new complex Z is formed when we added hydrochloric acid in this complex. The color of the solution changes, right? Write an equation for the formation of Z from the solution of this complex. Include the formula and charge of Z. So we have this complex Cu NH3 4 H2O 2 plus. An excess of hydrochloric acid is added. So that means now you have to memorize these equations, that when we add hydrochloric acid, 4 moles of hydrochloric acid will react with this complex. So that means 4 NH3, all the 6, basically chloridine is a larger ligand. Cl minus is a larger ligand as compared to water or NH3. So it will change the geometry of this complex. All the 6 ligands would be replaced by 4 of the chloridines. 6 ligands would be replaced by 4 chloridines. So 2 water molecules and 4 NH3, they will be replaced, and we get this complex, the Z, CuCl4. So geometry will change. From octahedral, it will convert into tetrahedral complex. So CuCl4, and now the charge would be copper was +2. This was +2. Cl is -1. So -1 into 4, -4, +2, -4. Overall charge would be -2. 4 NH3 molecules are released and 2 H2O. So this is the equation for this reaction. So you just have to memorize it, that whenever chloride replaces the water or NH3, all 6 would be replaced, and we get 4 chloridines. So name the type of the reaction when Z forms this complex. What type of reaction is happening? This is ligand substitution or ligand exchange reaction. Ligand exchange reaction. State the geometry of Z. So just remember that whenever we have chloridine, and if we have chloridine and the coordination number is 4, it is forming 4 dative bonds, and whenever we have a halide, coordination number is 4, the geometry will be tetrahedral. So we get a tetrahedral complex. And state the color of solution Z. Color of solution Z. So solution Z is this CuCl4 2 minus. So when copper forms a complex with chloride, or we can say tetrachlorocopper 2 ion, this gives a yellow colored solution. Again, you have to memorize this color. So this is a yellow colored solution. Now the last part of the question is, explain why the color of a solution of CuNH3 4H2O2 plus is different from the color of solution of Z. You should refer to the energies of orbitals involved in your answer. So this is an octahedral complex, and this is Z is a tetrahedral complex. And as I told you earlier, that in case of octahedral and tetrahedral complexes, when ligand approach, the splitting of d orbitals would be different. So that means energy gap would be different. So d orbitals split differently. The orbitals split differently, and the difference of energy between orbitals will be different. And if this different of if the energy is different, that means they would absorb different amount of light, and the transmitted color would also be different, right? So this is why we get different colors for both these complexes, because we have a different split of d orbitals for both the complexes. All right, so the next question is again from transition elements. And in this question, it is saying that an excess of aqueous ammonia is added to a solution containing the complex ion hexa-aqua cobalt 2 plus ion, right? So we have added excess of aqueous ammonia in this complex ion, right? And this is the chemical reaction. Complete the sentence to describe the color change that will be seen during this reaction. So the color change from now hexa-aqua cobalt 2 plus ion, this gives pink color solution, right? So the color changes from pink to, and this complex gives a brown color solution. So this color changes from pink to brown. So you have to memorize the color for the complexes of cobalt and copper. Write an expression for the stability constant of hexamine cobalt 2 plus ion. So we have to write the stability constant K stab equation for this reaction. And K stab or stability constant, this is basically a ratio between the concentration of a complex and its constituent ions at equilibrium, right? So K stab would be the concentration of NH3 2 plus and its constituent ions, and its constituent ions are COH2O6 2 plus NH3 6. So this is the K stab equation. The numerical value of K stab of this complex is 7.7 into 10 power 4, right? So this is the stability constant for the formation of hexamine cobalt 2 plus ion. What deduction about the properties of hexamine cobalt 2 plus ion and hexa-aqua cobalt 2 plus ion can be made from this K stab value? Right now, hexamine cobalt 2 plus ion is forming when hexa-aqua cobalt 2 plus ion reacts with ammonia, right? And we have a large value of K stab. And a large value of K stab means that this particular complex is more stable as compared to this particular complex, right? Because the value of K stab is high. So what deduction can we make about the properties of hexamine cobalt 2 plus ion and hexa-aqua cobalt 2 plus ion from this K stab value? A large value of K stab means CONH3 6 2 plus is more stable than COH2O6 2 plus, right? So it is more stable than the complex from which it is forming. All right, so the next question is oxygen can oxidize hexamine cobalt 2 plus ion into hexamine cobalt 3 plus ion under standard conditions in alkaline solution. So they're saying that oxygen can be used to oxidize this complex in which cobalt has a charge of +2 into this complex in which cobalt has a charge of +3 under standard conditions in alkaline solutions. And the equation for this, the redox equation for the cobalt 3 plus going into cobalt 2 plus, they have given us this equation and the E naught value as well. So this is the E naught value, that is 0.10 volt. Now the question is, use this information and the data booklet to calculate the E naught cell value for this oxidation of hexamine cobalt 2 plus ion. So basically we are oxidizing hexamine cobalt 2 plus ion into hexamine cobalt 3 plus ion. So this reaction is going backward, right? So we have to calculate the E naught cell for this oxidation of hexamine cobalt 2 plus ion. For this we have to find out the equation in which the equation of oxygen as an oxidizing agent under alkaline solutions. So we have to find the equation in data booklet. All right, so oxygen, okay, so here's the equations for oxygen. So this is the equation. You can see that oxygen is gaining electrons in alkalinic solution, right? We can use this equation as well, but this is in acidic medium, so this equation cannot be used. We will use this equation, and the E naught value for this equation is plus 0.40. So this is the E naught value plus 0.40, right? So we have to calculate the E naught cell, and the E naught for the equation for this equation is plus 0.10. And as cobalt hexamine cobalt 2 plus ion is being oxidized and oxygen is being acting as an oxidizing agent, right? So that means E naught cell would be E reduction minus E oxidation. So oxygen is being reduced, so E reduction would be plus 0.40 minus E oxidation is 0.10. So E naught cell is plus 0.30. This is the E naught cell. Right, now the next part of the question is, write an ionic equation for this oxidation of hexamine cobalt 2 plus ion. All right, so this is our desired equation, and in this equation you can see that we have 4 electrons, right? We have 4 electrons, and the equation which they have given us for hexamine cobalt 2 plus ion, in that equation we have 1 electron. So that means this equation will be multiplied by 4, because in final equation, in redox equations, we don't have to write the electron. So this would be 4, 4 and 4, and this becomes reactant side, because hexamine cobalt 2 plus ion, this is being oxidized into this. So that means this is the reactant side, and it is reacting with oxygen. So 4 electrons will be cancelled with 4 electrons. Now what we are left with on the reactant side, we have CO NH3 6 2 plus from this equation, and on the reactant side from this equation we have plus, and this is multiplied by 4. All right, O2 plus 2H2O, and then on the product side we have 4 CO NH3 6 3 plus, now it is oxidized, plus 4OH minus. So this is the desired ionic equation. All right, now the last part is predict by selecting suitable data from the data booklet whether oxygen can oxidize CO2 plus. Whether oxygen can oxidize CO2 plus in acidic solution in the absence of ammonia. Explain your answer. So now we have to find out the feasibility of another redox reaction in which whether oxygen can oxidize CO2 plus, only cobalt 2 plus ion, in acidic solution, this time in acidic solution in the absence of ammonia, right? So the equation which we will take this time will be oxygen as an oxidizing agent in acidic medium. So this is the equation in which oxygen is acting as an oxidizing agent in acidic medium, and the E naught value is plus 1.23. And just remember, to predict the feasibility of the reaction, the E naught for the oxidizing agent must be higher than the E naught for the substance being oxidized or the substance which is acting as a reducing agent. So the E naught for the oxidizing agent is plus 1.23. It must be higher than the E naught of cobalt 2 plus. So let's look at the E naught of cobalt 2 plus, which has to be oxidized. So here is cobalt 2 plus oxidizing into cobalt 3 plus, and its E naught value is plus 1.82, which is higher than plus 1.23, 1.82. So that means this reaction cannot happen because the E naught value of the oxidizing agent is lower than the E naught value of the reducing agent, right? So this reaction cannot happen because we get the E naught cell in negative, and if E naught cell is negative, that means the reaction cannot happen. So the answer to the question would be we have to predict whether by selecting the suitable data. So we said that the E naught value for the oxygen acting as an oxidizing agent to make 2H2O, the E naught value is plus 1.23, and the E naught value for CO3 plus, this is 1.82. So as this value is higher than the substance which has to be oxidized, its E naught value is much higher than the substance which has to be reduced. So as this value is higher, so that means reaction will not happen, right? No reaction will occur. All right, so okay, so the next question is now from organic chemistry. This is from benzene. The structure of benzene 1,3-dicarboxylic acid is shown. So this is benzene 1,3-dicarboxylic acid. 1, 2, 3. So first part of the question is state the empirical formula of benzene 1,3-dicarboxylic acid. Right, so we have to write the empirical formula of benzene 1,3-dicarboxylic acid. So first just find the molecular formula. So how many carbons we have? 1, 2, 3, 4, 5, 6, 7, 8. C8 hydrogen 1, 2, 3, 4, 5, 6, H6, and oxygens 1, 2, 3, 4. O4. So this is the molecular formula, C8H6O4, and if we simplify it, so this becomes 2, 3, and 4. So the empirical formula for benzene 1,3-dicarboxylic acid is C4H3O2. Okay, now the next part of the question is benzene 1,3-dicarboxylic acid is an isomer of benzene 1,4-dicarboxylic acid. Right, this is the structure of benzene 1,3-dicarboxylic acid, and it has an isomer which is benzene 1,4-dicarboxylic acid. These two isomers can be distinguished by C13 NMR spectroscopy. State the number of peaks in the C13 NMR spectrum of each compound. Right, so on a C13 NMR spectrum, the carbon atoms with the similar environment, they would give the same peak, right? So we have to find out the number of carbon atoms which have similar environment in both benzene 1,3-dicarboxylic acid and benzene 1,4-dicarboxylic acid, and this will give us the number of peaks. Okay, so in benzene 1,3-dicarboxylic acid, how many different carbons do we have? So if you just look at this structure, this carbon and this carbon, it has similar environment because both the carbon atoms are attached to two oxygen. On one side they have a double bonded oxygen, on the other side it is an OH group. Then they are attached directly to the ring, and between these two COOH there is one carbon here and 1, 2, 3. So that means these two carbons are similar, right? These two carbon atoms are similar. So this is one carbon environment, And then these two carbon atoms again are similar because they have the same environment as well, right? So this is the second peak, and then we have these two carbon atoms. They have the similar environment, third peak. Now this is a different carbon and this one is a different environment, because 4 and 5, if you look, so the fifth carbon, this carbon is attached to, I'm talking about this fifth carbon, this carbon is attached on both sides to a carbon which is directly attached to COOH. So fifth, the environment of fifth is different from fourth, because fourth carbon is attached to two CH groups. So that means fourth and fifth, they are two different environments. So in total, in benzene 1,3-dicarboxylic acid, we have 5 different carbon environments. So that means 5 different peaks. And now we have to calculate the number of peaks in benzene 1,4-dicarboxylic acid. For that, we have to draw the structure. So let's just draw benzene 1,4-dicarboxylic acid. So this is COOH. And carbon number 1, 2, 3, 4. This is carbon number 4, COOH, and a ring in the center. So this is benzene 1,4-dicarboxylic acid. Now let's just count the carbon environment. So these two carbons, they again have the similar environment. Again, they are attached to the same carbon atoms to the ring, and they have a plane of symmetry. So that means they would give the same peak. And these two carbon atoms, which are directly connected to the COOH group, these two carbons of the ring, which are directly connected to the COOH group, they have the same environment. So this is these two have same environment. And then these 4 carbon atoms, they have similar environment, right? These 4 carbon atoms, so they all would give same peak. So that means in benzene 1,4-dicarboxylic acid, the total number of peaks which we get on a C13 NMR is 3. All right. Now, the next question is benzene 1,3-dicarboxylic acid can be made by the 2-step synthesis shown below. This is benzene 1,3-dicarboxylic acid. This can be made in 2 steps. Step 1, step 2. Name compound P. So this is compound P, and we have to name this compound. So a benzene ring is attached directly to COOH. So this is benzoic acid. This is benzoic acid. And explain why the major product of this 2-step synthesis. Explain why the major product of this 2-step synthesis is benzene 1,3-dicarboxylic acid and not benzene 1,4-dicarboxylic acid, right? So why we are getting 1,3-dicarboxylic acid, why not 1,4-dicarboxylic acid? And the reason is, I hope you all know this thing, that in case of benzene, when we do substitution reactions, so one of the hydrogen would be replaced and we replace it with some group. So let's suppose this is the first substitution. So in first substitution, there is no priority. All the 6 carbon atoms are similar, so any hydrogen can be replaced. But once we are done with the first substitution, now this is carbon number 1, this is carbon number 2, 3, 4, 5, and 6. And now the second substituent which would attach to the ring, where it will attach to the ring, it depends on this X group, right? There are 2 different types of X, one which are 2 4 directors and the one which are 3 directors. And COOH is a 3 director, right? And how you can find out that whether it is a 3 director or a 2 4 director, you just have to look that the atom which is directly attached, in this case carbon is directly attached to the ring. So the atom which is directly attached to the ring, if it itself is directly attached to a highly electronegative atom, like in this case carbon is directly connected to oxygen, right? This carbon which is attached to the ring is directly attached to oxygen. So if the atom which is directly attached to the ring is itself attached to a highly electronegative atom, then most probably it would be a 3 director. So we can say that why we will get benzene 1, 2, 3. Why we get benzene 1,3-dicarboxylic acid, now not 1,4-dicarboxylic acid. The reason is that COOH is a 3 director. It directs the second substituent on third position. It directs the second substituent on third position. Right, so it is a 3-director. All right, now the next part of the question is the reagent used for step 1 are CH3COCl and AlCl3. Now step 1, whatever is the step 1, we have converted this compound P into compound Q. So in this step we have used the reagent which we have used is this CH3COCl, ethanoyl chloride and AlCl3. So these reagents give rise to this positive ion which reacts with compound P. So name the mechanism of this reaction. So basically this is electrophilic substitution. Benzene undergoes electrophilic substitution. This is acylation of benzene ring. And now the next part of the question is draw the mechanism of the reaction of this ethanoyl ion with the compound P. Include all relevant curly arrows and charges, the structure of the intermediate and the structure of compound Q. So this is our electrophile and it is attacking on the ring. So while drawing the mechanism, just remember this thing that the pi electrons, the delocalized pi electrons, these delocalized pi electrons of the ring, they will attack on this on this carbon atom, positively charged carbon atom. So you have to draw an arrow from the delocalized carbon atoms of the ring towards the positively charged carbon atom, right? So the delocalization would break and we would get this intermediate. And this is the hydrogen which was attached to the structure, and now this is attached to carbon number 3. All right, and the delocalization breaks partially, so we would draw a partial delocalization by this half circle and a positive charge in that, right? Next, to regain its delocalized pi electron system, to regain its stability, the hydrogen will be lost as a proton, and these two electrons, they would move back into the ring. So we will just draw an arrow, these two electrons into the ring. And finally, the structure which we get is delocalization again forms. And now we have on third carbon, we have the COCH and this is structure. So this is compound Q, right? This is compound Q. All right, now the next part and the last part of the question is suggest a reagent and conditions to convert compound Q into benzene 1,1,3-dicarboxylic acid in step 2. So we have to give the reagent, name of the reagent, and the conditions to convert compound Q. Now let me just draw the structure of compound Q here. So compound Q is on the third carbon we have a methyl ketone, right? And we are converting it into benzene 1,3-dicarboxylic acid. So this is benzene 1,3-dicarboxylic acid, right? So how can we convert a methyl ketone? I hope you remember this reaction from your AS level, that this is a methyl ketone and we have to convert it into a carboxylic acid. So how can we convert it, a methyl ketone into carboxylic acid? By reacting it with alkaline aqueous iodine. So when we react it with alkaline aqueous iodine with I2OH minus, so when we react it with alkaline aqueous iodine, this bond will break. We get iodoform CHI3, but we are not interested in this right now. This carbonyl group would be oxidized and it would convert into the salt, because we are doing it in acidic, in alkalinic medium. So first we get a salt, carboxylic salt, but we need carboxylic acid. So to convert it into carboxylic acid, next we would do acidification, right? We would add acid, which will convert the carboxylate salt into acid. So just remember this thing, that this bond will break and we get, first we get, let me just draw it here. So first we get this salt, C double bond O, O negative, right? Carboxylate ion. And when we acidify the solution, when we add H plus ions, these H plus ions will be gained by this O negative, and this convert into OH, and the negative charge would be lost. So we get our carboxylic acid, benzene 1,3-dicarboxylic acid. So the reagent that we will use in this reaction to convert this compound Q into benzene 1,3-dicarboxylic acid, the reagent which we used is alkaline aqueous iodine. Alkaline aqueous iodine 1, and then afterwards we do acidification, right? So we do acidification and we get benzene 1,3-dicarboxylic acid. Okay, so the next question is question number 8, and in this question saying that alanine and glutamic acid, and they have given us the formula for both these amino acids. Alanine and glutamic acid are two naturally occurring amino acids. Okay, so this is alanine. Alanine exists as two optical isomers. Draw three-dimensional structure of these two optical isomers. So we have to draw two isomers, optical isomers, and alanine is optically active because it contains this carbon, chiral carbon. It is attached to 4 different groups. So we have to draw enantiomers or optical isomers. Enantiomers are basically non-superimposable mirror images. So we have to draw non-superimposable mirror images, 3-dimensional. So C, let's say H, NH2, CH3. We're talking about this carbon, this is attached to an H, then NH2 and CH3, and finally CO2H. So CO2H. So this is the 3-dimensional structure of one of the enantiomers of alanine, and the other would be the non-superimposable image of this structure. So it would be CO2H, CH3 will shift on this side, and H will this shift on this side, and we have NH2. So these are two non-superimposable mirror images, or the optical isomers of alanine. Alright, now the next question is related to the NMR spectroscopy. The proton NMR spectrum of either alanine in D2O or glutamic acid in D2O is shown. So they have given us proton NMR spectrum, and this is in D2O. The solvent used is deuterium oxide, and we don't know whether it is alanine or glutamic acid. We have to find it out, right? So state whether this is the spectrum of alanine in D2O or the spectrum of glutamic acid in D2O. Explain your answer by reference to the number of peaks and splitting pattern. So we have to find out that whether it is the spectrum of alanine or glutamic acid in deuterium oxide, right? And we have to explain our answer based on the number of peaks and the splitting pattern. So first of all, let's just draw the structure of alanine and glutamic acid. So in alanine, we have 3 carbon atoms, 1, 2, 3, right? 3 carbon atoms, and we have an NH2 group and H. So this is the structure of alanine. And in glutamic acid, we have 1, 2, 3, 4, 5. Right, so basically this is CH. Let's just draw it here. CH, NH2, CO2H, and in the side chain we have a propanoic acid, CH2, CH2, COOH. Alright, so this is the structure of alanine, and this is the structure of glutamic acid. Okay, and the NMR spectrum that we have here, this is in D2O. So D2O is basically a solvent, and when we take the proton NMR in D2O, we know this thing that proton exchange occurs. So proton exchange occurs, so that means all those protons of OH group and NH2 group, they will disappear. So that means the peak due to this proton would not be observed. The peak due to this proton will not be observed, and in glutamic acid the peak due to this proton will not be observed, and the peak due to this proton and this proton, right? So these protons which are attached to either oxygen or these protons which are either attached to nitrogen, they will be exchanged with deuterium, right? And deuterium does not give a peak on a proton NMR, so these protons will not be present on a proton NMR when we perform it with deuterium oxide. So this means the proton NMR of alanine, if we talk about alanine in D2O, we only would be able to get two peaks, one due to this protons, one due to these protons, and one due to this proton, right? And let's just find out the splitting pattern and the number of peaks. So we get two peaks in case of alanine. In case of alanine, we get two peaks. In case of glutamic acid, how many peaks would we get? 1, 2, and 3, right? So in case of alanine, we get 2 peaks, and in case of glutamic acid, we get 3 peaks. We have 3 different proton environments in glutamic acid, and we have 2 different proton environments in alanine when we perform the NMR in deuterium oxide. Alright, the peaks due to NH2 and the peaks due to OH would disappear, so we only get 2 peaks for alanine and we only get 3 peaks for glutamic acid. And on the spectrum which we have here, this has only 2 peaks, right? This is only 1 and 2. So that means it is alanine, but let's just confirm it with the splitting pattern as well, right? So the splitting pattern of this CH3, splitting pattern is due to the protons attached to the neighboring carbon atom. So this CH3, it has this neighboring carbon atom which has 1 proton, and the splitting pattern is number of hydrogens attached to the neighboring carbon plus 1. So the CH3 has 1 proton on the neighboring carbon atom, so that would be 1 plus 1 would be equal to 2. So we get a duplet. This is duplet, and this proton, it would give a splitting pattern of, because the carbon it is attached to, its neighboring carbon atom has 3 protons, right? So this will give 3 plus 1, which is equals to 4, right? So this is the splitting pattern of 4 if you observe it. Yes, so this is 1, 2, 3, 4. So we get a splitting pattern of 4, right? So yes, this is the NMR spectrum of alanine. So now we have to write down our answer. So this is the spectrum of alanine. This is the spectrum of alanine, as it has 2 different proton environments. So it will give will give 2 peaks. Right, it will give 2 peaks with the splitting pattern of duplet and quartet. All right, so this would be the answer. Now the next question is the mass spectrum of glutamic acid is NH2 is obtained, right? This is glutamic acid, its mass spectrum is obtained. State the mass to charge value of the molecular ion peak in this spectrum. So molecular ion peak is when the molecule as a whole loses a proton, loses an electron, so it gets positively charged. So whatever is the molecular mass of the compound, that would be the mass to charge value of the molecular ion peak. So we just have to calculate the molecular mass of glutamic acid, and the molecular mass of glutamic acid is 147, right? If you just calculate it, that would be NH2 means 14, 15 and 16 plus carbon CH 12 plus 1 13 plus 13 14 15 CH2 14, again a CH2 14 and CO2H, carbon 12, oxygen 2 oxygen 32 plus 1, so this would be 45 and 45. Right, so if you add all of them, it becomes 147. All right, this is 147. The spectrum has peaks with mass to charge value of 88 and 131. Draw the structure of the ions responsible for these peaks. Right, so we have two fragments here, 88 and 131. So we have to draw the structure of the responsible ions which give these peaks. So we have the molecular formula is NH2. So let's just calculate it. The MR, NH2, that is 16 plus CH 13, 16 plus 13, then we have CH2, that is 14. So 16 plus 13 plus 14, that is equals to 43. And if we add COOH into it, so we get 88. So that means 88 is due to NH2, CH, and one of the CH2 from the branch, and CO2H. Right, so this would be the fragment for the mass spec for the peak at 88. So for the next peak 131, the overall mass, we know that overall mass is 147, and if we subtract 131 from it, we get 16. So that means the fragment lost is 16, which is NH2. So we get just simply our formula, that would be CH, just remove NH2 from your formula, so this becomes CH2, CH2, CO2H, CO2H. So this is the peak at 131. This is due to this fragment. All right. Now the next part of the question is, at pH 11, alanine exists as this negative ion. Right? Alanine pH 11 means basic pH. So in basic pH, all the protons would be lost. Right? So we have this particular ion for alanine, and glutamic acid exists is, again, this is also in negative ionic form. So a mixture of alanine and glutamic acid at pH 11 is subjected to electrophoresis. State how the mixture can be maintained at pH 11 during electrophoresis. So pH is maintained through a buffer solution. So by making a buffer. Alright, so pH will be maintained by making a buffer. Describe a fully labeled diagram for the apparatus that would be used to carry out this electrophoresis. Right, the diagram to carry out the electrophoresis, your diagram should include the position of the mixture of alanine and glutamic acid at the start of the electrophoresis experiment. So we have to draw the diagram which would be at the start of the electrophoresis process. So let's suppose this is a gel coated slide, right? And it is connected to DC supply. Alright, so this is plus terminal, this is minus terminal, so this would be plus and this would be minus. And let's say this would be the, because we have to include the position of the mixture of alanine and glutamic acid at the start of the electrophoresis. So let's say this would be at the center. So we say that this is the position of the alanine and glutamic acid at the start of the process. Right, now just label the diagram. So this is the gel coated slide, and we have mixture of alanine and glutamic acid. This is the mixture of alanine and glutamic acid, and this is our DC supply. Right, so this is the diagram at the start of the electrophoresis experiment. Alright, next part of the question is identify the electrode that each amino acid travels toward during electrophoresis at pH 11. So at pH 11, both the particles, they are in negative ion formation, right? They both are in negative ion formation. So that means they both will move towards the positive electrode, and positive electrode is anode. So both of them will move towards the positive electrode. Right, so they would move toward, alanine would move towards the positive electrode because they are negatively charged, or we can simply say that towards the anode. So positive electrode or towards, and similarly for glutamic acid, it would also move towards the positive electrode. Now the last part of the question is, in a particular electrophoresis experiment at pH 11, the glutamic acid travels 3.4 cm, alanine travels a shorter distance. Explain the factors that account for the difference in the distance traveled. So glutamic acid travels, this is the ion, now this is the ion of glutamic acid, and glutamic acid has overall charge -1, it has an overall charge of -2, and alanine has an overall charge of -1. So because it has an overall charge of -2, so it would travel at a faster rate, and this is what they are telling us here, that the glutamic acid is travel 3.4 cm, alanine travels a shorter distance. The factors that account for the difference in the distance travel. So the first factor is that alanine is -1 ion and glutamic acid is -2. So it travels more. Right? And the other factor is the mass. Alanine is a smaller molecule, as you can see that it is a smaller molecule as compared to glutamic acid. So alanine is lighter, but charge is the dominating factor. So that's why glutamic acid is traveling more as compared to alanine, but still mass is a factor, so we have to write it here as well, that alanine has a smaller MR, it is a lighter particle. So if the charge would be same, then heavier particle would diffuse slow and lighter particle will diffuse more, right? But here, because glutamic acid, although it is a heavier particle, but as it has a charge of -2, so that's why it is traveling more as compared to alanine, right? So the next question, question number 9 is butylamine. This is the structure of butylamine, can be synthesized from different organic compounds by using suitable reagents. Each reaction involves one step, right? So all these reactions are one-step reactions. Complete the table to describe 3 different syntheses. So we have to write three different syntheses of butylamine, which involve only one step, right? One step reactions. So one of the three syntheses should involve a nucleophilic substitution reaction. All right, so like we have to prepare butylamine through three different ways. One of them must involve nucleophilic substitution reaction, one step reaction. So that means that would be from alkyl halide, right, halogenoalkane. So if we take butyl halide or one chlorobutane or one bromobutane, so let's suppose that would be CH3, CH2, CH2, CH2Cl. This is one chlorobutane, primary alkyl halide. This will react through SN2 mechanism, which is a single step reaction, right? So this will react with ammonia. Reagents and conditions, it will react with ammonia, nucleophilic substitution. NH3 will act as a nucleophile, ethanolic ammonia, heated in a sealed tube or vessel. So condition would be heated in a sealed tube. All right. Now, the starting organic compound for each synthesis should contain a different functional group. A different reagent should be used for each synthesis. So one way of preparing butylamine is from halogenoalkanes. We already have written that reaction. Now, another way of preparing butylamine in a single step reaction is hydrolysis, reduction of cyanides, right? Reduction of cyanides or reduction of nitriles. So if we take CH3, CH2, CH2, CN, butane nitrile. So this nitrile group CN, this will get reduced in the presence of a suitable reducing agent. So the suitable reducing agent for the reduction of cyanides, that could be either LiAlH4, or we can use active metal plus ethanol, right? So this could be the reducing agent. So both carbon and nitrogen, they will gain two hydrogens, CH2 this becomes, and it becomes NH2. So we get our desired product, that is butylamine. And the third way of preparing butylamine in a single step reaction, that would be from butanamide, reduction of butanamide. If we take butanamide, CH3, CH2, CH2, C double bond O, NH2, right? So this is butanamide, and for the reduction of butanamide, we can use the same reducing agents, LiAlH4 or sodium plus ethanol. So this amide group, it would get reduced. This carbon would lose its oxygen and gains two hydrogen. So this becomes CH2NH2, right? So these are the three different reactions through which we can prepare butylamine in a single step reaction, right? And the next part of this question is related to the basic nature of ammonia and its derivatives. So compare and explain the relative basicities of ammonia, butylamine, and phenylamine, right? So we have three different compounds: ammonia, which is NH3. Then we have butylamine, which is CH3, CH2, 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 NH2. And we have phenylamine. And phenylamine is when we have NH2 group directly attached to benzene ring. So this is phenylamine, right? So these three structures, and we have to compare and explain the basicities of ammonia. So like you all have learned this thing in theory section, that amines are more basic than ammonia, right? So most basic would be butylamine. Butylamine is most basic. Then arylamines. This is an arylamine. Arylamines are less basic as compared to ammonia. Both alkyl amines and aryl amines are derivatives of ammonia. Alkyl amines are more basic than ammonia and aryl amines are less basic. So after butylamine, ammonia would be the second option and least basic would be phenylamine. Right, this would be least basic. Now we have to explain our answer as well. So the basic nature, all these are weak bases, and the strength of a weak base, it depends on how easily it can gain proton. Like let's suppose nitrogen in NH3, it is attached to 3 hydrogen atoms and it has a lone pair available. So the availability of this lone pair makes ammonia basic, as through this lone pair it can accept proton, an H plus ion. And how easily it gains this H plus, it will decide the strength of the base, right? That how strong the base is. So we are saying that butylamine is more basic than ammonia. That means it has more availability of this lone pair. And why it has more availability of this lone pair? Like nitrogen has this lone pair available, right? In NH2, we're talking about this NH2, it has this lone pair available, and it also has a chain of carbon atom connected to it. And the chain of carbon atom, or these alkyl groups, they have a tendency of losing electron. They have a tendency of releasing electron, which we call positive inductive effect. So basically nitrogen, due to its high electronegative nature, it withdraws electron from the alkyl groups, right? And this is called the positive inductive effect. So basically due to positive inductive effect, a small amount of electron density move towards nitrogen, due to which the negative charge intensity on nitrogen would increase. And when the negative charge intensity on nitrogen would increase, this lone pair would become more available for proton acceptance. So we can say that in case of ammonia, there are no R groups attached to nitrogen, only hydrogen atoms. In case of amines, we have R group attached, which due to its positive inductive effect makes the lone pair more available for proton acceptance. So that's why amines are more basic than ammonia. And why aryl amines are less basic than ammonia? In case of aryl amines, if we talk about aryl amines, this nitrogen again has a lone pair, but it is on the same plane on which the p orbitals of this benzene ring lies. So the lone pair of nitrogen, it becomes part of the delocalization of ring, which makes it less available for proton acceptance, right? So basically in case of aryl amines, the lone pair on nitrogen, it becomes part of delocalization, which makes it less available for proton acceptance and hence less basic, right? So now let's write the answer. So we're saying that butylamine is more basic because first of all, the basicity is related to the proton acceptance. Right, it is related to proton acceptance or the availability of lone pair. So in case of butylamine, lone pair is more available due to electron releasing effect of R group or due to positive inductive effect, right? And in phenylamine, it is less available as it becomes part of ring delocalization, delocalized pi electrons, right? So this provides the structure more stability, but makes it less basic. All right, so this is the end of this question. And now the last question of this paper is complete the table to show the structure of the organic products from each reaction of phenol. So they have given us some reaction of phenol and we have to draw the structure of the organic products. So this is a simple question. Phenol reacting with NaOH. Phenol can react with metals or metal hydroxides or strong alkalis. So when phenol reacts with a strong alkali, we get sodium phenoxide, right? Salt. We get sodium phenoxide, or you can just simply draw the phenoxide ion, or you can draw the structure of sodium phenoxide. Now the second reaction is phenol reacting with sodium. It would be the same product because again phenol will act as an acid and sodium will displace the H of OH group. So we get sodium phenoxide, right? And the next reaction is azodi formation. We have this diazonium ion, phenyl diazonium ion reacting with phenol at 4 degrees centigrade in the presence of base. So we get the azodi formation. So let's suppose this is the structure of phenol, right? OH. And in azodi formation, the azo group, it attached on the 4th position, on 4th carbon. So this is carbon number 1, 2, 3. So this is carbon number 4. So on 4th position, we get nitrogen attached, and now we have this structure. So this would be the structure we get when phenol reacts with phenyl diazonium ion below 10 degrees centigrade in alkalinic medium, right? And the last question is an excess of phenol when reacts with this compound. So we have benzene ring attached to 2 acyl groups on both sides. So on both sides, esterification would occur. Phenol will react with both the acyl groups. So Cl would be lost from this side. Cl would be lost from this side, and from phenol, H would be lost. So HCl will be released as a small molecule and we get a diester. So we get this diester, C double bond O, O, C, 6H5. So this would be the structure of the diester that we get. And last question is identify 2 reactions from the table in which ethanol would behave in a similar way to phenol, right? These are 4 reactions of phenol. Now they're asking us to identify 2 reactions in which ethanol will behave in a similar manner as phenol is reacting. So alcohols, they cannot react with alkalis, but they can react with metals. So reaction number 2, both phenol and alcohol will react in a similar manner. Azodi formation, alcohols cannot undergo this reaction, but they can form esters. So yes, 2 and 4. Reaction 2 and reaction 4, both alcohols and phenol will react in a similar manner. All right, so this is the end of this paper.